So we'll take a small problem. Okay, so we're going to design a digital high pass filter. Okay, so see the question: digital high pass filter. Okay, we have to design a digital high pass filter. How we are going to design? By using bilinear transformation. Bilinear transformation. Okay, that's what is given in the question. Monotonous in passband. Whenever they indicate monotonous in passband, it is means it is a Butterworth filter. Butterworth filter. Okay, it's a Butterworth. So it should be monotonous in passband and stopband. Okay, what else is given? Cutoff frequency. Cutoff frequency is 1000 Hertz. Cutoff frequency is 1000 Hertz. Whenever cutoff frequency is given, it is nothing but I take it as FP, 1000 Hertz. Okay, and whenever the word cutoff frequency comes, it means alpha p is equal to 3 decibels. That is the meaning whenever you mention it as cutoff. Okay, alpha p is given 3 decibels. Then this is your alpha s is given 10 decibels. Okay, and the corresponding fs is given as 350 hertz. Okay, so first we'll convert these frequencies into radians. So omega p is equal to this is fp is 1000, so 2 pi into 1000, so this value is 2000 pi radians per second. Similarly, omega s is equal to 2 pi into 350, it becomes 700 pi radians per second. So we have omega p, omega s, alpha p, alpha s. Okay, but whenever we want to design a digital filter, the first step is to design a analog filter. So since we are going to apply bilinear transformation, the first step will be we need to do pre-warping. Okay, we have to pre-warp the filter frequencies to avoid warping effect. So the formula for pre-warping is 2 by t tan omega t by 2. Okay, t is given in the question. If you see, sampling frequency is 5000 hertz. Sampling frequency, okay, t is equal to 1 by f, it is 1 by 5000. Okay, so t is actually 2 into 10 power minus 4 seconds. That is what is given in the question. Okay, so t is 2 into 10 power minus 4 seconds. Fine. Now if you actually solve for it, so we'll first find omega p. Omega p is equal to 2 by we have to check this value, 2 into 10 power 2 into 10 power minus 4. Okay, so it is tan of omega p is 2000 pi into 2 into 10 power minus 4 divided by 2. So this becomes 10 power 4 tan. Okay, 2 gets cancelled, so we'll be getting 0.2 pi. If we actually solve for this, we'll get it as 7265 radians per second. Similarly, omega s is equal to 2 by 2 into 10 power minus 4 tan of, here it is 700 pi into 2 into 10 power minus 4 by 2. So that actually gives you 10 power 4 into, so same thing, here it is 0.07 pi, which gives you 2235 radians per second. Okay, so this is my omega p and omega s. With this I have to design my analog transfer function first. Okay, so what I'll do is, my desired high pass filter will have something look like this. The characteristics actually look like this. It's an high pass filter. Okay, so 3 decibel cutoff. Okay, 3 decibels cutoff at 7265 radians per second, and minus 10 dB cutoff at 2235 radians per second. Okay, so that's what is given here. Okay, so once we want to design this high pass, but the first step is always designing an equivalent low pass filter. Okay, so we'll just can take like this. So this 10 decibels will come here. Okay, so at 10 decibels it will be actually reversed. At 10 decibels it will be 7265, and this will become 2235, that is at minus 3 decibels. So we'll take this as omega p, this as omega s, and we'll be designing our, so here it is omega p is here, this is omega p and omega s, this is for high pass filter. But to design the analog high pass filter, first we have to design the analog low pass filter, and then only we can go to a converting that into an high pass filter. Okay, so first step, we already know that we are going to design a Butterworth filter. So we'll take a new page, and for Butterworth filter, to find the transfer function you need the order. Okay, n should be greater than or equal to log of square root of 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1 by log of omega s by omega p. Okay, so n should be greater than or equal to log of square root of alpha s is 10 decibels. Okay, so 0.1 into 10 minus 1 divided by 10 power 0.3 minus 1 divided by log of 7265 by 2235. Right, so n should be greater than or equal to log of 3 by log of 3.25, and if you solve for that, you will be getting n should be greater than or equal to 0.932 or n equal to 1. So order of the transfer function is 1. Okay, so if n equal to 1, okay, you can find the poles. So poles is e power sk is equal to e power j phi k, again phi k is equal to pi by 2 plus 2k minus 1, k is equal to 1 only. Okay, so it is pi by 2, so it is pi. So s1 is equal to e power j pi, or it is cos pi minus j sin pi, it is equal to 1. You have only one pole. Okay, so my h of s is equal to 1 by s plus 1. This is my normalized analog transfer function. This normalized transfer function has to be converted into a high pass filter first. Okay, to convert this h of s into an high pass filter, we have to apply the transformation s as omega c by s. What is the cutoff frequency for your high pass filter? 7265 by s. So in my original transfer function, replace, okay, to get the analog transfer function, in my h of s, replace s by 7265 by s. So it will become 7265 by s plus 1, or it becomes s by s plus 7265. This is my analog transfer function for my high pass filter. Okay, now we have to convert this into a digital transfer function. How to convert it? To get my h of z, from my HA of Z, that my analog transfer function, I have to replace S equal to 2 by T into 1 minus Z inverse by 1 plus Z inverse. Okay, that's how you are applying bilinear transformation. So HA of S is nothing but S by S plus 7265, and you apply S is equal to 2 by 2 into 10 power minus 4 into 1 minus Z inverse by 1 plus Z inverse. Okay, so if I apply this, what will happen? So here instead of yes, you're going to apply this one. Okay, so this 1000, it comes to the top, I'll get it as 10 power minus 4. Okay, so we'll get 10 power 4 into 1 minus Z inverse by 1 plus Z inverse by 10 power 4 into 1 minus Z inverse by 1 plus Z inverse plus 7265, and if you solve for this, you'll get it as 0.5792 into 1 minus Z inverse divided by 1 minus, that is, you have to cross multiply, add, and do all those subtractions and all. Finally you will be getting something like this: 1584 Z inverse. This is my final H of Z. Okay, so to design your high pass filter, digital filter, what are the steps? Just we'll go back. So from the question, FC FP is given. Okay, FC is nothing but FP here, and FS is given, alpha P alpha S is given. Okay, so first step, you will convert that into omega P into omega S. These frequencies are converted into radians. Then you need to do the pre-warping to design, that is, you get the analog frequencies by pre-warping your digital frequencies. So pre-warp frequencies are there, and this is my desired high pass filter. To design my high pass filter, first I have to design my low pass filter. Once I start with designing my low pass filter, first I will find the order of the filter. I found the order as 1, and based on that I found my normalized transfer function for omega C is equal to 1 radians per second. This low pass transfer function, normalized low pass, is transformed into an high pass by using this transformation. By using this transformation, I convert my normalized low pass into an high pass. So this is my high pass transfer function. After that, I need to convert that into my digital transfer function by using bilinear transformation, 2 by T into 1 minus Z inverse by 1 plus. Just you're going to substitute, and I'll be getting my, so this is my final digital high pass transfer function, okay, for the given specifications. Thank you.